to introduce Lenka Negrete, who is going to tell us about Cloudy being used to model the BLR in quasars.
Okay, well, all these days about quasars, and I'm going to talk about the use that we did of Cloudy to model the Broadland region physical conditions in quasars. And, well, as you already know, for the Martin talk, quasars emit in a very, very small region, and type 2 quasars emit very broad lines from type 1. From 1,000 to 20,000 kilometers per second. And also, as Martin said, the profiles that we can see are very, very different. And why we see a very different kind of spectra is because the physical conditions inside quasar are intrinsically different. And that together with the orientation angle, we see different spectra. I'm going to show you this for spectra. This is the optical region for different quasar spectra. This is H beta. And what I want to emphasize here is that, as you can see, the full width of maximum of all these spectra are very different. And not only that, also Martin said that iron 2, it's very different, and in Deborah's talk, she will talk more about this ion. This is the UV spectra for the same object as previous. This is the carbon 4 line. And as you see, also the profile are very, very different. This one is very symmetric, but we have here one that is completely blue shifted, and we have very different profiles. Here is the 1900 blend, which we have here carbon 3, silicon 3, aluminum 3, and silicon 4. I will show you later. And, well, how can we study all these very different kind of spectra? Well, there is work of Sulentic, Marciani, and Dultzin that they made this four-dimensional eigenvector 1 to try to see the spectral characteristics of quasar. And this 4-dimension involves this 4-dimension. The full width of maximum of H beta, which is a prototype of a low ionization line, the radio of the equivalent width of iron 2 over H beta, the gamma soft excess, and the carbon 4 blue shift. Carbon 4 is a prototype of high ionization line. And here I show you the optical plane of this eigenvector 1. This is the RFE, and this is the full width of maximum of H beta. And, well, in 2000, they say, well, we see that we can split all these points into population. Population A, which is lower than 4,000 kilometers per second, the H beta, and point B, the full width of H beta larger than 4,000 kilometers per second. And, well, this is the optical plane. They have the other dimensions. And they propose that this diagram could be a HR diagram for quasars. This is the 3 authors. And later, they started to study. This was first empirical result, but then they started to study which are the physical parameters that are involved in this sequence. And, well, this main sequence has these trends. Here we have the largest black hole masses, the largest ionization parameter. This is the viewing angle that we are looking in this way. So no, sorry, in this way, edge on. In this way, this is the accretion rate, the electron density, and this is the radioluminosity to mass. And we propose the use of CLOSI to measure these two parameters, the ionization parameter and the density of the broadline region for individual objects. And why we want those two parameters? Well, because if we have U and NE, from the ionization parameter formula, we can have the size of the broadline region. This is the product U and H. Well, is electronic density, or equivalently hydrogen density. And this is important for high redshift quasars. For low redshift quasar, we have a well-studied correlation. Well, we have also direct measurement of the size of the broadline region, which is the reverberation mapping. But for high redshift quasars, we don't have it. And the way to measure the size of the broadline region, we will call it the photoionization method. And if we know the size of the broadline region, if we assume that the gas is virialized, we can retrieve the black hole mass. Our spectra, our sample spectra are 8 quasars observed with the VLT force. We fitted these lines in the UV spectrum, carbon 4, the blend silicon 4 over plus oxygen 4. This is the 1900 blend, carbon 3, silicon 3, aluminum 3, and silicon 2. In the when we compute the ionization parameter and density, we exclude carbon 3 because we know that it is emitted in a lower density region, because its critical density is 10 to the 9, 9.5. And I would like to show you an example of how we fit the carbon 4 profile. This fit is very important because as we want to measure, as we want to compute the black hole masses, we need to isolate the virial core component from the other components that are emitted in different regions. Well, this is carbon 4. This is the rest frame of carbon 4. As you see, this line has a blue shift. So first we fit the virialized component, and then we fit the blue shifted component. The dotted line is the sum of these two components, and the lower panel are the residuals. We think that this blue shifted component is produced in an outflow that are moving toward us and is dominated by radiation pressure. And finally, we fit other lines that are under this line, which is helium-2, silicon-2. And, well, this is for carbon 4. And for the 1900 blend, if you see, there is a very blended profile. We first fit the iron-2, which is not very strong in the UV, but we fit here iron-3, which is very strong, especially in carbon-3 area. Then we fit carbon-3 in its rest frame. This is the rest frame of carbon-3. Then silicon-3, aluminum-3, silicon-2, which is a weak line. In the end, we didn't take it into account because it introduces the largest uncertainties. And finally, for this example, we fitted some absorption lines. And well, we fitted all our 8 spectra. This is the spectra that I already showed you. This one, I would like to emphasize that meanwhile this one has a blue shifted component, in this profile we see that the profile has a red wing, and it could be fitted a very broad component redshifted that could be interpreted that gas that is going to the black hole, is inflow the black hole. And well, with those we use the line intensity, the core component line intensity, to use it in the cloudy simulations. And well, the cloudy simulation, the initial condition that we use is the quasar continuum of Matthews and Ferland, the column density to 10 to the 23 and 10 to the 25 centimeters per area. The metallicity that we use, these 4 metallicities, 1 solar, 2 solar, 5 solar, and 5 solar, with an overabundance of silicon aluminum. This due to supernova contribution. And we did a grid of the density and ionization parameter from this in this area in intervals of 0.25. And the results are the following. Here we have several radios. This, for example, is aluminum 3 over silicon 3. This is carbon 3 over aluminum 3. This is silicon 4 over carbon 4, and so on. And, well, as I already told you, with the line intensities, we did these radios, and we choose the isocontour which belongs to the value. For example, for aluminum 3 over silicon 3, well, the logarithm, the value is minus 0.36. So this is the contour that belongs to this value, and so on for the other line radios. And we put them all together, and we see that we have here a crossing point. And with this crossing point, we can retrieve the density and the ionization parameter. And we do the same for the rest of the objects. And we see that we have 2 objects that the crossing point are not very well. This is the cloudy simulation for 1 solar metallicity, and for these 2 cases, let's say the pink and the green cases, that we see, well, this is not, this radio silicon 4 over carbon 4 is below the crossing point. For those 2 cases, we tried with other metallicities. This is 5 solar and 5 solar plus overabundance, and we see that in this case, the crossing point is very good. And for the green case, we see that the agreement improves for 5 solar metallicity with abundance. Those are the results for our 8 objects. This is the average of density and ionization parameter. And as you see, the spread of for 1 solar metallicity, the spread is not so large, neither for the density or the ionization parameter. Here I have the size of the Broadland region and the black hole masses that are fairly similar. And well, with these results, we want to calibrate with other methods. We want to calibrate our photoionization method with direct measurements. We did this work for 14 quasar spectra at very low redshift, 0.24. The reverberation mapping is just to measure the time delay that it takes the continuum variation, and then we measure the time where the broad line varies. And this is other empirical relationship that is related the size of the broadline region to the luminosity of the quasar. And I'm not going to show you these feats. I'm going to show you only the results. For these low redshift quasars, for 1 solar metallicity, the difference of hydrogen density and ionization parameter is larger than for the high redshift quasars. These are the average values for density, 11.88, and for ionization parameter is 2. And here, this is the logarithm of the size of the broadline region versus the logarithm of the reverberation mapping. And here we have that it correlates very well. Well, comparing with this empirical relation, well, the dark points are our comparison of the reverberation mapping, and the white dots are comparing with this empirical correlation, and it also correlates very well at low redshift. And this gives us the confidence that we can use our method to measure accurately the size of the broadline region and also the masses for high redshift quasars. And finally, I'm going to show you here the correlation mass. This is using our method versus the mass computed by the reverberation mapping size, and also correlates very well. And this one is a comparison of the mass of the reverberation mapping versus the mass of this relation, the mass black hole luminosity. And both correlations are quite good. In fact, our correlation is better. And well, as a conclusion, we develop a method that is based in a photoionization that allows us to compute the size of the broadline region in a very independent way of the reverberation mapping and this empirical relationship. This is important because at high redshift, the correlation luminosity size is not well calibrated and cannot be applied to determine black hole masses. Also, at high redshift, we cannot see absorption lines in order to measure the mass of the black hole, applying the sigma mass correlation. And well, our method is important because we can, as I already told you, we can measure accurately, we can measure the size of the broadline region. And one thing that I would like to highlight is that our method to be applicable, we need to isolate the core broad component only. Otherwise, we could have biases in the computation. And the average value for the samples at large redshift, the density is larger than in lower redshift quasars, and the ionization parameter also differs. This is the product. I show you the product because it's the product that we use in the RBLR equation. And that's it. Thank you.
Very nice that being able to get spectroscopic black hole masses with simple epochs is very important. The reverberation measurement shows highly stratified, so different lines come from different areas. How does your method deal with that?
We use H-beta to have the measurement. In fact, the reverberation, yes, they use several lines, H-beta, H-alpha, and so on, and we take the average of the broad lines. We exclude the high ionization lines, for example, carbon-4 and other lines, and we use only that.
Actually, I have a question. Your high redshift samples seem to have very similar properties. How were they selected?
Well, at high redshift, we can see we have a bias in a high redshift. I didn't mention it. Thank you for the question. The principal reason that we have here different conditions is that at high redshift we have a bias. We see only the highest luminosity quasars, and our sample were selected to have both populations, population A and population B, to have a narrow, full width have maximum is narrow and also broad. They are mixed in order to, well, yes. And we try to choose for all the populations.
And let's thank Lenka again. Martínez-Paredes on the mid-infrared diagnostic diagram of AGNs.
Oops.
Just be a moment or so whilst we decouple. Give you a signal with 5 minutes left.
Okay, thank you. Okay, the talk that I'm going to give you today, or in this talk, I'm going to show you the main results that we obtained from analyze the most typical mid-infrared emission lines for starbursts and active galaxies. This work was led by Marcio Melendez, who was my advisor, and together with Claudio Mendoza when I was a master student in Venezuela. But currently, I am a recent postdoc at the Radio Astronomy Institute of Loughnane in Morelia. And during the last year, I have been working on those Titorus models in quasars and Eulers. No? So I have not followed the recent publication in this field, but I want to bring this talk into this meeting. So the motivation for this work was come from the mid-infrared diagnostic diagram proposed by Weber et al. In 2010, in which they uses the neon-3, neon-2, and oxygen-4 mid-infrared emission lines to separate the AGN contribution, black points in this diagram, from the mid-infrared emission from starburst galaxies, the others one. In this part of the diagram are the most extreme starburst galaxy. So we use the neon-2 is a low is an emission line with a low ionization potential, typical for a starburst galaxy, while the oxygen-4 is an emission line with a high ionization potential respect to neon-2 that is typical for active galaxies. While the neon-3 is an emission line with an ionization potential, with an intermediate ionization potential that offers a perspective in which we can have the contribution, at the same time, the contribution for the AGN and starburst in the host galaxy. The AGN sample, or the CFIRS sample that we represent here, was selected but has a hard X-ray flux. In this way, this is an unbiased sample. The aim of our work is to define
a new theoretical demarcation line for the mid-infrared, infrared, and optical diagrams that take into account the minimum and maximum contribution of the AGN to the emission lines spectrum as predicted from photoionization model of the mid-infrared diagrams, where the emission line are less affected by extinction. So to do that, we use the photoionization code clouding, and we start by define the AGN photoionization source and the starburst. For the AGN, we assume a broken power law and these typical abundances. While for the starburst, we use the starburst 99 code developed by Negrete et al., and we assume two star formation law. An instantaneous with a total stellar mass of 1 times 10 to the 6 solar masses, and a continuous with a star formation rate equal to 1 solar masses per year. In both cases, we assume double initial mass function of Krupa in order to take into account the low and high stellar masses and the Padova tracks, stellar evolution models, and 3 metallicities. This model covers a range, a stellar age from 10 to the 6 to 10 to the 8 year. Then we vary the ionization parameter and the hydrogen density between typical range found in narrow line region in Cepheid galaxies, and here this is the flow of the ionizing photons. Earth is the distance to the clouds, and C is the speed of the light. We also assume a constant density model with a hydrogen column density equal 10 to the 21 centimeter to -2 that allow us to have different, to have abundant and radiation matter. So we found that for AGNs, or for Cepheid galaxies, only a two-zone model grids, I mean a model that combines or that mix a region with low hydrogen density, a high ionization parameter, and a region with a high hydrogen density and low ionization parameter is the better combination of models that can produce the emission lines in the most active galaxies. In this plot, are the black and red points. This AGN are AGN with a strong starburst component. For the starburst modeling, we found that a single zone model with the range of ionization parameter and this hydrogen density, assuming a star formation burst and solar metallicity, is the best model that reproduces the starburst, this extreme starburst galaxy. But this model fails in reproduce the emission line of these starburst galaxies. In this case, we need include a physical mechanism that produce efficiently the emission of oxygen for, essentially, for example, Wolf-Rayet stars. However, we found that a combination of two-zone models grids, I mean, any combination of an instantaneous star formation burst within this range of ionization parameter, solar metallicity, and a range that covers a range of solar age between 10 to the 6 and 10 to the 8 years, and hydrogen densities are the best model that produce these ratios in starburst galaxies. However, we know that in this case we have a lot of free parameters. These galaxies, the galaxies, this starburst galaxy that are out of the shade region in which we produce the observed region have evidence, some of them has evidence of a AGN or of a weak AGN. And then we, using the physical condition derived from the mid-infrared diagram, we predict the optical emission line, the typical optical emission line, oxygen 3, H beta, nitrogen 2, and H alpha to build a minimal demarcation line. Here is this one that this lower bounded demarcation line represents or is produced with a ionization parameter of -1.5, where the oxygen 4 surpasses the ionization fraction of oxygen 3. In this case, we found that our definition produced nearly a 40% more AGN than the Kaufman demarcation line, and it's consistent with the demarcation lines of Stasin's cancer 06, that is this, and this is the Kaufman. And the line of the maximum AGN contribution, this one, to the optical spectrum is given by a set of conditions adopted in our AGN model from mid-infrared. So our conclusion is that we successfully reproduced the AGN region in a mid-infrared diagnostic diagram with a two-zone model, which is a combination of a low ionization and high density and a region with a low density and high ionization. Our single model sun starburst model are a good fit to the extreme starburst region, but fail in reproduce the starburst, the typical H2 region with in the bottom region of the mid-infrared diagram. Then we found that a two-zone starburst approximation is the better approximation. We investigate the optical prediction for our two-zone AGN mid-infrared photoionization grid and found that the physical condition that produce the neon 2 also produce a small fraction of nitrogen 2. And in this way, we define a new theoretical demarcation line for the minimal AGN contribution to this optical diagnostic diagram. And we define also a maximum AGN contribution in the oxygen 3, H beta, and nitrogen 2, H alpha diagram based on a two-zone approximation represented by the combination of any two regions within a range of parameters that maximize the emission of these optical lines. So that's all.
I have a question. There is this fuzzy sound. What about liners?
Well, liners, in principle, are here.
That's region. What I thought.
Yeah.
Whatever. Yeah. Okay.
So the usual method to get starburst versus AGN is the PAW emission. How does this compare with that diagnostic?
Sorry?
The PAW, the PAH emission.
About the PAH, well, the neon 3 and neon 2 are similar diagnostic that pass emission. Like but I'm not sure to understand the question.
So it's consistent with the detection of the PAHs.
Yeah, there is pass in this system, yes.
again. And the last speaker before our tea break is Loughnane, who is here.
That would work better. That would. Okay. Well, thank you for the organizer to invite me to this wonderful event, first of all. I'm really enjoying it. It'd be good to kill the lights a little bit. So amazingly, I was looking at NASA ADS, and both Gary has published many papers. I've published a few papers as well. And we have absolutely no overlap. We never publish, even though we have large collaboration, we don't have any papers in common, which is really quite amazing, because it feels like I'm a collaborator of Gary, because Gary, of course, is a close collaborator of my former advisor, Don Osterbach, but also it's just that my students and I have been using Cloudy for, I think, more than 25 years now, and so I feel like we should be collaborators. So I inserted some of the papers, work that I've done with Cloudy in here, both at the beginning and at the end, and between will be something a bit different. But I chose the sort of the most general title I could find. But what I really will be talking about is EGN line diagnostics and quasar feedback, and how these EGN line diagnostics we actually heard quite a bit about already. But I'll expand on them and give you a little bit of a historical perspective, how these EGN diagnostics can be used to constrain quasar feedback, which is really my main interest nowadays. This is actually a picture, I'll come back to it, but this is an example, Marking 231, which has already been mentioned, where we actually see a really powerful, spectacular quasar outflow. We really think it's quasar-driven, and we think it actually it can actually cause quite a bit of damage to the host galaxy. So I'll come back to that. This is, of course, not the data. This is the artistic rendition of the outflow. I've had that question before, so I want to set things, be clear. So EGN line diagnostics, my story started in mid-'80s when Don Osterbach and I dared to try to improve the spectral classification of emission line galaxies and try to make it more robust to various effects, flux collaboration, but also reddening issues, etc. And so I came across this paper by Gary and Haggai Netzer in '83 with this number of citation. This is actually the most highly cited first author paper by Gary that doesn't have the word cloudy in it, in the title. It really is a wonderful paper. It really helped me understand the theory behind these line ratios. This is figure 1 of the paper, which shows the line ratio with respect to H beta, and the various strong optical and UV lines. I don't know if this was cloudy 33, Gary. Do you know? I'm putting you on the spot. So this is a bit faint, but we were actually interested, Osterbach and I were interested in the strongest line in the optical, which are shown here. We were not particularly interested in 3727 because we thought it was too affected by dust. So we didn't actually include it in our classification. But it really shows how the highly ionized material increases with ionization parameter, but not the case for the low ionization lines. So it really already crystallized the idea that we really need a two-dimensional parameter space, both involving the high ionization and low ionization. Of course, we know now that the key thing about AGN is that the ionizing spectrum has a strong fraction of high energy photons beyond 54 eV, quite a bit beyond that. And so, existence of highly ionized zone in the material facing the AGN. So you have an enhancement of the high ionization lines. But you also have enhancement of the low ionization lines because the X-ray penetrates through that column of material deposit energy there, increase the temperature. And so anything that is emitted in this partially ionized zone, like O1, sulfur 2, etc., will be enhanced also. So this was really the idea behind this spectral classification, to try to emphasize the difference between AGN and H2 region, where in AGN, the low ionization lines and the high ionization lines are enhanced, relative to H alpha, for instance, or H beta. This plot has been shown before. This was the version that we published in '87. But the point is we showed the Ferlin-Netzer models here with ionization parameter from 1 log of -1.5 to -4. And the idea in this paper was really to see if the liners, the low ionization nuclear emitting regions in the center of galaxies, can be explained through forced ionization by the AGN. And the conclusion of that paper is that yes, it's quite possible. Shocks also can do it. And it turns out now that it really is a mixed bag. The liners are a mixed bag. So the idea of the classification is we chose line ratios that involve strong lines, unblended lines. Of course, all these rules apply to the mid-infrared diagnostic that we heard about, and also the far infrared. They should involve strong unblended lines that emphasize the difference between H2 and AGN, of course. But the long wavelength to avoid reddening or try to minimize reddening. And also line ratios that have similar wavelengths. And so again, they're not very sensitive to reddening. So this diagram appears in both in BPT first and also in our paper. And then this particular diagram involving the sulfur 2 lines did not appear in the BPT because it involved IDS, image detector scanner. How many of you know what an image detector scanner is? There will be an age bias here. I did use an image detector scanner, even in my early days. And so it doesn't go beyond H alpha or nitrogen 2. And so the sulfur 2 was not involved in the BPT. So we introduced this in that particular paper. And again, the Ferlin-Netzer solar abundance fit very well through the CFIRS, but also through the liners. And that was point of the paper. So the main diagrams that have been used in the optical were in our 1987 paper involving the nitrogen 2, the sulfur 2, and the O1, and that's been used in the literature now quite a bit. And we used it in the late 1990s. We applied it to infrared bright galaxies. Especially the so-called ultraluminous infrared galaxies that have quasar-like luminosity. I became really interested in them because we thought that they might be proto-quasars. So hundreds or so of them, and so this is the sort of numbers we were getting in terms of number of targets that can be put in these diagrams, hundreds or so. And in this particular paper, we found that among ULERGs, about a third of them have AGN. And then if you go at even higher infrared luminosity, it becomes about a half. There's a dependence on luminosity. Of course, this is 20th century data. Things have changed 21st century. Sloan came up with 100,000 galaxies. So this is taken from Lisa Cooley's 2006 paper. It really shows the beautiful difference between H2 star-forming galaxies, basically a star-forming abundance sequence from low abundance to high abundance, and then the AGN, and then this diagonal line, which is a mixing line between AGN and star-forming galaxies, with different fraction of star formation in them as you go from pure star-forming galaxies to pure AGN galaxies. And the liners fall where they used to. Basically, it's a very similar classification scheme, but you have the advantage of having 100,000 galaxies. It's really beautiful paper. And of course, more recently, with the advance of multi-object infrared spectrograph, it's now possible to do this same sort of work, but higher redshift. Redshift beyond 0.6, when H-alpha and nitrogen and sulfur 2 shifts out in the near infrared, but all the way to redshift 2 now. And that's just one paper that I picked, one image that I picked, where basically the same diagram, but now the points are the redshift 2 objects. And it's definitely work in progress. This is all the way to 2016 now. There's quite a bit of debate, but the conclusion, the main conclusion is in the nitrogen 2 diagram, the objects at redshift 2 are shifted to the right. They have larger N2 to H alpha than at redshift 0. But surprisingly, that's not seen in the sulfur 2 diagram. So it's quite a bit of a puzzle. So there's a number of possibilities that have been suggested by Lisa Cooley in 2015, and Shapley in 2015, and Chuck Steidel in collaboration in 2016, that involve larger ionization parameters, harder EUV, which perhaps is not too surprising if you have lower stellar emitticity at redshift 2. But they also require binaries to make it really hard. To try to explain the difference between these two diagrams, the shift in this diagram, but not the shift, no shift in this one, they talk about enhancement of nitrogen over oxygen. And then there's also possibility of supersolar oxygen over iron. Basically to explain, they're able to fit these data with O over H of 0.5, which is actually pretty large for redshift 2. But it has to be low stellar emitticity, and most of the opacity in the stars comes from iron, so they need to reduce the iron without having to reduce the oxygen. So you get a supersolar O over iron. So there's still a work in progress. Quite a bit of debate about that. Okay, so this is the optical line diagnostics. I don't think I need to justify the need to go to a longer wavelength just to look at the column density in H alpha for optical depth of 1. You really only get a column density of 10 to the 21. And so you're really very sensitive to dust. And this was one of the criticism of the work that has been done in the optical is, what about dust? Even though the line ratios are insensitive to dust, it could be that you're really only seeing the surface of the material. You're not seeing deep down where the AGN is. So by going to the near infrared, you gain 1 order of magnitude. To the mid-infrared, you get another order of magnitude, to 2 orders of magnitude with respect to H alpha. And in the far infrared, 3 orders of magnitude with respect to H alpha. This is really a huge gain. Spitzer, we were lucky that Spitzer, of course, was launched. And so we observe the same object we observe in the optical, but we did it with a Spitzer. This is a paper that we published in 2009. So mid-infrared spectroscopy. And this is sort of a summary of the diversity of the spectra that one gets on ULERGs, local ULERGs and quasars. There's just a large number of diagnostics that I've already mentioned, the fine structural lines, iron, neon 5, oxygen 4, and the Pi emission, but also the curvature of the continuum is, there's a wide variety between Seyfert's and H2 galaxies. And so those ingredients can be used to determine what is the fraction of the luminosity in these objects that is produced by the AGN. So that was the purpose of this particular paper. And so we used 6 different methods to try to quantify that using line ratios of O4 and neon 5, also the pi equivalent width, and various measures of the slope at different wavelengths. And they gave actually consistent results to within plus or minus 15%. And so we found that applying this method, we found that 39% of the boloelectric luminosity in ULARGs, in local ULARGs, is produced by AGN, which is pretty significant. There's a trend with optical spectra, which is shown here. This is this alpha AGN percentage as a function of just optical spectra. So in other words, what this means is if you detect a CFR2 in a ULARG, on average, it has a higher AGN fraction than an H2 galaxy, which is actually comforting for optical spectroscopists like me originally. But there's a huge variation within H2 galaxies. And so you really need the mid-infrared to pin down this alpha AGN, the AGN fraction. Now, the quasars, by the way, fall up here at 90% or so and above. These objects are mergers, and so we have a merger sequence. We can compare this fraction of AGN with respect to the phase of the merger, and we find a correlation. As the merger takes place, these are Milky Way type galaxy versus M31 colliding with each other. So these are major mergers. And as the merger takes place, the fraction of AGN, the fraction of the boloelectric luminosity that's produced by the AGN, increase as the merger takes place. The extinction peaks at intermediate stages. This is based on the silicate, the depth of the silicate feature at 10 micron. So these results were consistent with the idea that ULARGs, which are the merger of two major galaxies, similar mass, eventually results in a production of a quasar. And the extinction peaks in the middle, and at later stage, the dust is disappear, it becomes transformed into stars, or it's ejected out of the galaxy. But they're scattered, so one really needs a large sample. I mean, for us, a large sample meant 100 galaxies. Because they're scattered, there's definitely stochastic random variation in the black hole accretion rate, but there is a trend as the merger takes place, and that we can only see that with a number of 120 galaxies or so. Unfortunately, there's not that many local ULARGs, period. We're limited by the numbers. Things change drastically as higher redshift. I wanted to mention, there's been a discussion of the far infrared. I just wanted to mention the idea of the Mocha gas as well. It's there in abundance. And one perhaps could use the properties of the Mocha gas to try to constrain the AGN fraction, look for obscured AGN, obscure quasars in these systems. This was from Urshel Spire in this collaboration of Hercules, where this is the first object we observed was Mark 231, the brightest, the easiest, the best. And this is how it looked like. You notice all in red those CO transition. It's just a nice, beautiful, regular forest or picket fence of CO transition. Again, in this 2010 paper, everything looked pretty rosy, and we were really optimistic that we could use the CO ladder, the so-called CO ladder. This is intensity or luminosity as a function of upper level of the CO transition to constrain the fraction of the luminosity that's produced by the AGN. In this case, Mark 231, we use X-ray dominated X-ray dominated regions, and to claim that this portion was perhaps produced by the AGN. Unfortunately, as is often the case, first object is great, but then if you include the whole sample, things gets a bit more murky. And that's exactly what happens. We published a paper last year where the full sample, about 30 objects, this is again luminosity of the CO versus upper level of the transition. We just, astronomers like to classify things, class 1, class 2, and then class 3. Mark 231 fall in this category where the CO ladder doesn't fall much at higher transition. But unfortunately, this classification, or the ratio of the intensity of the lines here versus where at the peak, do not depend on AGN fraction, on the AGN fraction that we determine from the mid-infrared. So scratch that idea, unfortunately. Unless, by miracle, what we're actually seeing here is that some of these objects that we did not detect at the mid-infrared, the AGN, comes out in the far infrared, possibly. There's a correlation with the 60 to 100 micron color, and there's also a correlation with the CO line width, which is, in this case, is dominated by rotation. So it's basically a measure of the mass of the galaxy. So the most massive objects have these highly excited CO transition. So nothing to do, at least not directly, with the AGN fraction, unfortunately. This has been also shown in another paper we published using POX now, extending the upper level all the way to J of 30. And again, it stays flat, but this level of flatness does not depend on whether or not there's a strong AGN in these objects or not. There's another parameters going on here. So unfortunately, the CO doesn't seem to be a good ingredient, a good AGN diagnostic indicator, which is unfortunate given ALMA, et cetera. Okay, so let me talk a little bit about quasar feedback. So we're using what we learned from the mid-infrared, this AGN fraction, and try to apply to the issue of whether or not the quasar is affecting the host. And so go back in time a little bit. We now know that the neutral gas in the system and also the molecular gas, about 5 to 10% of it is actually highly disturbed. It's not just rotating, it's outflowing, or it's just turbulent. The neutral gas, we just use our old friend, the sodium line, the sodium doublet, going back to 2002, a thesis by Dave Rupke at Maryland. So the sodium doublet, this is at redshift 0, this is the stellar component, and then there's material that is highly blue shifted in absorption now. So there's unambiguous signature of outflow of the neutral gas. The ionization potential of sodium is 5-ish, so it really is a neutral gas. It's the probe of the neutral gas. So what's remarkable, at least that was remarkable for us at the time, is that a very large fraction of these objects have these outflow. So 20% for the objects that have star formation rate of order 10, like M82-ish, but that becomes 75% for objects like Eulergs, like star formation rate above 100 solar masses per year. And we think this is a geometry in the sense that in the objects at star formation rate of 10, the outflow looks like this, but for the Eulergs, it's just wider angle. It covers a wider field of view, a larger fraction of 4 pi. These outflows are spatially resolved. We had long slit data, even in these older paper. And so we were actually able to estimate the mass outflow rates, compare that with the star formation rate we were getting of order unity, but a very large scatter of an order of magnitude. Many of the simulations, large-scale numerical simulation, cosmological simulation, assume 1, by the way. But what we observe is that there's a very large scatter. Just using the kinematics, the velocity, and the escape velocity that we could estimate from these objects, we got the escape fraction of the gas of being 5 to 20%, but that assumed no halo drag. And we now know that these objects have corona or halo, gaseous halos, that are metal-rich and contain, in some cases, almost as much oxygen in the halo that in the galaxy themselves. We now also have new, I can't go into the detail, but we also now have very deep Chandra data of some of these objects, where we detect the highly ionized corona in these objects on scale of 100 kiloparsecs. And it contains a huge amount of oxygen. It's actually alpha element enriched. So this was circa to 2010. So the last few years, my group and many others, which I didn't list here, have been using IFU to study these objects. Again, using the sodium in absorption. This was the first paper we published, Marking 231 again. So this is the footprint of the IFU, and this is the velocity field that we derive in this footprint. And notice the scale, everything is blue shifted. The red is at a blue shift of minus 300 kilometers per second, all the way to minus 1,300 kilometers per second. So everything we saw in the sodium is blue shifted in our direction. It's quite symmetric with respect to the QSO, basically 4 pi as seen from our point of view. And the dimensions of this outflow is limited to 2 to 3 kiloparsecs simply because we just run out. The light is against the galaxy host, and it becomes too faint. So we just run out of signal to noise. But it probably extends even further. So it's a lower limit. The velocities are in excess of 1,000 kilometers per second. And so we have spatial information. We can derive masses. And this is the sort of mass outflow rates that we derive. Of order unity compared with the star formation rate. But the mechanical energy, because given those high velocities, is very large. It's impossible, basically, for the starburst to drive this outflow. The starburst itself does not have enough energy to drive the outflow, even if it's 100% thermalization efficiency. While the AGN, you only need a small fraction of the molecular luminosity to just capture 0.5%, and you'll be able to drive the outflow. Now, about the same time, Herschel was launched, and perhaps, arguably, one of the most surprising discovery of Herschel was the discovery of P Cygni profile in these same systems. This is, again, one example, magnitude 31. I've been showing only magnitude 31, but we now have 40 objects like this that show P Cygni profiles in Eulergs. And so this is looking at the OH transition, 119 transition. This is ground state transition. What's remarkable is the fact that this wing extends to 1,000 kilometers per second. Right? This is 0. This is about 1,000 kilometers per second. So this is the molecular gas in the galaxy moving out of the galaxy at 1,000 kilometers per second. It was really a big surprise to most of us. We were not expecting that. Even though we saw the neutral gas moving at this sort of velocity, we did not expect the molecular gas also to move at that same velocity. So this has become a cottage industry. The field has really exploded. There's been a lot, and I only listed a small fraction of the paper. But Herschel surveys, our group has led the charge in basically doing a survey of Eulergs. We found P Cygni profile in about 70% of these objects. So these massive fast outflow is the rule rather than the exception. 70% of these objects have these fast outflow. And these data, the Herschel data, have been supplemented by millimeter wave interferometric survey using the CO line in emission, kiloparsecs, spatially resolved. And so again, I mentioned that 70% of the local Eulers have these molecular winds, implying a widened opening angle of the outflow. Otherwise, we wouldn't detect them, right? This isn't P Cygni profile. The velocities, this is 50%, 84 percentile, and Vmax. These are the sort of velocity of the molecular gas. And these are typical size, kiloparsec size. The mass alpha rates range from 10 to up to 1,000 solar masses for the most extreme Eulergs. So this is a very large number. The momentum rates are large also. If one thinks of pushing the material, the molecular gas, using radiation pressure, we have a problem, right? Because the number is all the way to 20 times the radiation pressure in the infrared, which is the dominant term of just radiation on dust. There's plenty of energy coming out of these objects to drive these outflow, but momentum-wise, there's a problem. So it turns out the molecular gas that we had neglected all these years is the most energetically dominant phase of these outflow. So that's a lesson, perhaps, for the more distant objects that will definitely be gas-rich as well, where molecular outflow are likely to take place as well. We see trends with star formation rate and AGN luminosity that suggest that we're seeing starburst and quasar feedback in action. I'll just show you a couple pictures of that, where this is a paper by Myra Stone, who's a student at Maryland doing a PhD. This is the V50, the centroid velocity of the OH versus AGN luminosity. And there's a nice trend. As the AGN luminosity increases, become quasar-like, we're starting to see these massive outflows. The same thing is true also. It's actually even more visible when we look at the wing of the lines. So this was kinematics. If you look at the dynamics, the mass outflow rates, this is from CO now, versus LAGN, there's also a beautiful trend where sort of a threshold, this is for local object, gaseous system, when the AGN is quasar-like, there's many of these objects as molecular outflows. These objects here are just essentially pure starbursts. So the outflows that we detect here are driven by the starburst. So it really is a two-dimensional parameter space. You have the AGN, and you have the starburst. If the AGN is very powerful, it will drive extreme molecular outflow. But the same thing, if the AGN is 0, but they have a powerful starburst, you will also drive molecular outflows, like in MED2, for instance. So perhaps some of you in the audience wonder how does nature drive these molecular outflows? And it really is an open issue, so I don't have an answer here. Many of the numerical simulation can drive clouds, neutral molecular clouds, all the way to a velocity of 1,000 kilometers per second on the scale of a kiloparsec. It just gets destroyed before it gets there and reach that velocity. So one possibility is an AGN wind, which is radiation pressure driven, impacts on the ISM and produce a high velocity shock, completely ionize the material, very high temperature. It becomes so high temperature that it doesn't emit very efficiently. And so it becomes an adiabatic hot bubble. So you create a hot bubble near the center of the galaxy that is the piston to drive these molecular outflows. Now the question is, what happened after that? So that possibility is the ISM, the shocked ISM, eventually cool down, fragment, become thermally unstable, and produce those clumps, becomes neutral clouds, and then becomes molecular clouds that we detect. So that's one possibility. One question, though, is do we detect these nuclear AGN winds in these systems? Because that's the requirement. So just recently, we published a paper in Nature by Tom Bessie, which I won't go into the detail here, but that's an X-ray wind. We detected an X-ray wind in one of these objects where we had detected a molecular outflows. We're comparing the energetics. It actually matched very well with these energy-driven outflow models that are listed here. But I don't think we need to go in the X-ray all the time. We think that there might be optical and UV signature of these outflow in the nucleus of these objects. And we know that, in fact. So if we go back to our old friend Martínez-Paredes, there's plenty of signature of nuclear wind in the system, in the optical and UV spectrum. We can go back all the way 40 years ago. Boxenberg, 1977, showed actually a beautiful spectrum, optical spectrum of this object, which showed broad blue-shifted sodium, calcium 2, and helium 1, 3889. And we observed it with Keck 30 years later. In 5 minutes, got similar signal to noise, but basically we're getting to the same conclusion as Boxenberg and Klubbers came. So in the optical, there's plenty of signature of an outflow. This is systemic is 0. This is minus 4,000 or a bit more than minus 4,000 kilometers per second. In the near UV, there's also a signature of an outflow in absorption. This is from HST FOSS and HST STIS. From the recent data, but there's also some data that dates back to 1995 that detected this outflow. Again, similar velocity of in excess of 4,000 kilometers per second from magnesium 1, magnesium 2, and a forest of iron 2 here, iron 2 and iron 2 excited. And what was remarkable, this is what we did in 2013, is we observed this object with COS in the far UV, which had not been done before because this was not sensitive enough. And what we detected is everything was in emission. So in the optical, it was in absorption. In the near UV, it was also in absorption at this sort of velocity. But in the far UV, it was all in emission. This is how Lyman alpha looks like here, compared with H alpha, and compare with the absorption feature. So it's centroid velocity of minus 3,500 kilometers per second. Comparing Lyman alpha and emission, compare with the near UV lines that were obtained at the same time now. These near UV lines are obtained at the same time as Lyman alpha in this 2016 paper. And then finally, the other lines in the far UV, Lyman alpha, carbon 2, carbon 3, definitely detected, and carbon 4 definitely detected as well. Again, all blue shifted to 4,000 kilometers per second, but in emission. So this was really a puzzle. In the optical and the near UV, the absorption line, this outflow is in absorption, but in the far UV, it's in emission. There's a lot more behind that story that I'm saying, but just because the SCD is also really quite spectacular. But so the end results of that paper is the fact that what we think is going on is summarized in this picture. So first thing I should mention to you, which I didn't mention yet, is that Markov 231 has a high Eddington ratio. So the Eddington ratio is about 1, close to 1, plus or minus 0.5. So when the Eddington ratio is large, photon trapping becomes important. The photon are trapped within the accretion disk, within the accretion flow, and it puffs up. It becomes geometrically thick. So this is what's shown in this picture. These sort of accretion disks, thick accretion disks, are called slim disk. So this is what we try to represent here, which means that there is a funnel in these disks. And so the ionization radiation is not as isotropic. It really is a funnel. There's a radiation beam and so it reduced the high ionization lines. Like carbon 4 in Markov 231 and some of these other objects is reduced. So it's all consistent. There's also radio flares in the system that have been detected in 2013, which seems to suggest they're blazar-like, where we're actually looking pretty close, not quite down the throat, but close to it. So we think that we're looking at this structure along these sort of line of sight. Not quite down the throat, but pretty close. So there's a constraint there as well. So in this picture, there's the sort of standard broad emission line region that is in the disk. But there's also this outflow, and this is what's producing the absorption line in the optical and near UV. But we don't see it in absorption. These clouds are actually emitted emitting the far UV. So there has to be, these clouds have sodium. So we use cloudy to constrain some of the parameters of these clouds. This is the sort of numbers that also Fred mentioned. It's basically the same models that we run. Column density, AV in the clouds, so that we have sodium of order 1 or 2. These columns, not quite as extreme as what Fred was mentioning. Ionization parameter. And so we're able to put a constraint on the distance of these clouds. But the point is, these absorption line outflowing clouds have dust in them. And they're opaque in the far UV. So we can't see through them. And we can't see through them. It's hiding anything that comes through here. We're not able, in the far UV, to see the disk broad emission line region. There's many more clouds than was shown here. So all we see is any emission from these clouds on the surface. We see these Lyman alpha, blue shifted Lyman alpha and carbon 3. But at longer wavelength, the clouds become thin, and we see the absorption, and we start to see also the broadline emission from the disk. So it becomes more and more symmetric. H alpha is just a beautiful symmetric profile, but not the case for Lyman alpha. So we were able to put dynamics and then compare that with the predictions from how to drive a molecular outflows, and the numbers are consistent to within an order of magnitude. Okay, so let me summarize. So I want to emphasize how useful cloudy was in the old days, and still is very much so, in understanding, theoretically, what's going on with the behavior of the line ratio as a function of the various parameters, and which line ratios to use. What are the best line ratios to use to discriminate between starbursts and AGN, this method has now been extended to the mid-infrared, where we can actually quantify not only if an object has an AGN or not, but also to determine the fraction of the bolometric luminosity that is produced by the AGN, which is a bit more quantitative. I list a number of rules, simple rules here that we should all use, also the mid-infrared and the far infrared as new instruments comes along. So we use these the results from the AGN diagnostics to show that in ULERGs, local ULERGs, that quasar feedback is in action. These are the number we derive in terms of scale. The mass alpha rates, which are really very large, up to 1,000 solar masses per year, which imply a depletion time scale of about 10 million years in these objects, if it stays that way. Probably it peters out, but it can be as short as 10 million years. Here's the maximum velocity, the momentum. So these momenta suggest that they're not momentum-driven outflow, but they're energy-driven outflows. And the best candidate for that are the nuclear AGN winds that we're starting to detect in the X-ray and also in the optical UV. And I know this question was brought up this morning about the impact that these alpha may have on the host galaxy. I think we're starting to see that, actually, because we're starting to detect. I didn't really show data. If you're interested, I have another slide after that, where we actually see corona around these objects that are metal-enriched. And so the material from supernova type 2 must have been redistributed out into the halo. And so these winds may have done that. They're the best candidate for doing that. Okay, I'll stop here. Thank you.
Long ago, Ed Salpeter used to have a very useful viewpoint toward astrophysics, and that is, you try to identify relevant dimensionless parameters. For example, and the point was they had to be related to physics. For example, there are very profound reasons why stars have 10 to the 57 baryons. That's the kind of thing I mean. So in line with that when we invented the ionization parameter, we didn't have in mind originally that it would just be a classification parameter at random. We had ulterior motives. For example, the earliest hope for this was that in the older Neolithic primitive Stone Age models with ionization, it seemed to be the ionization parameter seemed to be indicating that the pressures of the gas involved were something of the order of 1/10 the pressure of radiation. Now, when you have a number like 1/10 that appears, it's not an accident. Now, that's just a historical thing that's probably long past, but the idea is that when you look at something like an ionization parameter, you should hope not just that it's a convenient way of describing objects, but that there be some simple and very fundamental reason why it has numbers in that range directly related to, for example, pressures and energy densities. Yeah. It should be inevitable.
Yeah, I think this is a very good point, actually, you're making. And so there's a whole discussion that I didn't have here that talks about pressure and why the line ratios in AGN are so similar among each other. Right? They could be all over the place. They could really populate the full ionization parameter, which they don't. They really are close to similar ionization parameter. And that's because radiation pressure is actually it's bigger than 0.1 nowadays. It's closer to 1. It really is an important ingredient in all the narrow line region models that now are out there. Yeah, so you're making a very good point. And I think the people who work in this area now have appreciated this point only recently, I would say the last 5 years only, because that's when radiation pressure was included properly and quantitatively, and they were able to compare it with. Yeah, I think it got lost in between. Probably when I started getting involved, I lost it. And then, but now, it really has come back where they talk about the pressure and how it compares, how the various terms compare. And it's important to the fact, it explains better the fact that they're all pretty similar in many ways. Not only the narrow line region, but also the extended narrow line region, even the broad line region. Some people have argued that that term is important.
Okay, I think we should continue the discussion over coffee. It's about that time, and please come back at 4 o'clock. Thank you again to the speaker. Okay. All right, you just keep trying. Yes.
I hear all discussion because it's break. No, this is the and this is the
Okay.
Yes, it's ready.
Hello? Hello? Yep, it works.
Putting here.
Oh, very good. Okay. Excellent.
If you like to mute, you press fast. Green is open.
Very good.
No muevas. Nada más pon la contraseña y ya. Okay. A las 5. Que vean.
Hola. Yeah, works. Oh, yes, I know.
This is a message.
All the time. Actually, we're going to have to get her Saturday evening, and everybody was at home on Saturday. I actually went to the fish recommended fish over at 7 o'clock.
Oh, okay.
I slightly misremembered. I thought it was 4 o'clock.
Oh, I see. Okay.
Okay.
Welcome.
So we're just going to wait a few minutes because I think I brought you back too early. I thought it was 4 o'clock instead of 4:15, so we'll wait just 5 minutes, make sure everybody comes in. And that means you have a bit longer at the end before the buses leave to have chat. I didn't want to start without her. Sorry, I was starting a bit early.
Okay, yes.
Is our first speaker here? We had him a moment ago, but he seems to have... Oh, here he is. Good. So I'd like to introduce Robert Loughnane from Ireland originally, who's going to tell us about something completely different from the previous talks.
Yes, totally off topic. First of all, thank you to the organizing committee for letting me give this talk. I work at IRIA, the Institute of Radio Astronomy and Astrophysics in Maryland, with Enrique Vasquez Simedini and his PhD student, Raul Naranjo Romero. My talk is on the synthetic spectral signatures in hierarchical collapsing gas. There's a brief overview of the talk. First of all, I'll cover some of the background material. Then I'll consider the radial velocity profile in such cores, low mass cores. I'll then consider the simulation details of Naranjo Romero's paper in 2015, the radio transfer details that were used to create the synthetic spectra. Then I'll look at the analysis of the synthetic spectra using the Hill 5 analytical model from De Vries and Myers 2005. Finally, some selected results, the ratio of the TB to TR, and the Mardonis parameter, Mardonis et al. 1997. Finally, some concluding remarks. Molecular clouds, giant molecular clouds, generally are supersonically turbulent. Until recently, Richard Kutcher has shown that they are not magnetically supported. These are the cores now, the molecular cores within the small-scale cores, because they are magnetically supercritical. So the magnetic field is not a support mechanism that inhibits their collapse. From the gravitoturbulent viewpoint, molecular clouds are supported against collapse by turbulence. This is from Mark Hayer's paper for 2009. Unfortunately, elements from the magnetic support scenario have crossed into the gravitoturbulent scenario. One of these is the fact that the cores, low mass cores, and high mass cores, intermediate mass cores, evolve quasi-statically. In other words, they undergo a phase where nothing is happening in the pre-stellar phase. This has been supported by observations of the Bonner-Ebert-like density profiles. We know that the Bonner-Ebert sphere is the solution to the hydrostatic Loughnane equation. So this is where this comes. So the whole point of this talk is to devolve that or destroy it. The questions that arise from our work is, how can cores be quasi-static since they are produced in what is essentially a supersonically turbulent medium? A couple of complications to cover. First of all, it's a genes stable confined configuration. If it's genes stable confined, it has to have a supporting or confining medium. How can that be the case? What we would then need is a two-phase structure. A two-phase structure, since at the subparsec scale, is unrealistic. Even in a one-phase medium, you cannot have a stable scenario. So a two-phase medium is even more unstable. Also, how can a hydrostatic configuration arise in the first place and then accrete quasi-statically before then collapsing? It doesn't seem to be realistic. Evolving configurations tend to form. They then accrete through shocks. Shocks are formed by the turbulent motions. Before they collapse due to their mass exceeding the gene's mass, they expand and then become unstable. They therefore collapse and never at all undergo a quasi-static stage. So the argument that we're posing here is that the quasi-static stage is a myth. It's a myth that's arisen from observations of low mass cores. So a possible answer to this is the global hierarchical collapse of molecular clouds. First put forward by Booker and Hartmann in 2007, also covered by Enrique in 2007, 2009, and recently covered by all three of us in Romero's paper from last year. In this picture, molecular clouds are turbulent. This is due to the several or more turbulent instabilities which bring about their construction. They're strongly genes unstable since the mass of the molecular cloud is many times the molecular genes mass, or the genes mass. Gas entering the molecular cloud undergoes a phase transition whereby warm diffuse atomic gas transitions into dense cold gas. What happens is the density increases and the temperature goes down by a factor of 100. This results in a reduction in the gene's mass by 10,000, Gomez and Vasquez in 2014. So clouds are all the time globally contracting. Their gene's mass goes down since the average density increases. This is with a roughly constant temperature. Small-scale fluctuations are created from the turbulence, and they naturally undergo collapse when the overall the mass of the fluctuation exceeds the gene's mass. So let's cover the simulation from Naranjo-Romero's paper, 2015. It consists of the numerical simulation of the collapse of a local near gene's mass fluctuation in a many gene's mass background medium. The background medium has a density of 10 to the 4 per cubic centimeter. What's important is that we don't consider the collapse past the protostellar construction. So there's no star produced in this simulation. The endpoint is the construction of the star, or the time steps coming up to that. So the collapse is limited to the prestellar stage with the collapse center of the background medium outside the box. That's very important here. So the whole simulation is mimicking, if you will, a fluctuation in the midst of a globally contracting molecular cloud. This is similar to Richard Larson's work in 1969, but the difference is that the fluctuation sits on a uniform, genes unstable background medium. The main features of the work in Raoul's paper were that the simulation developed the Bonner-Ebert-like profile quite consistently, quite naturally, even though the molecular cloud itself and the fluctuation are not in equilibrium. So the whole quasi-static picture seems lopsided. Also, like Larson's work and Penston's work in 1969, the core collapse is characterized by an outside-in velocity profile, whereby the outer material is at a higher velocity than the inner material. The inner material has a linearly radially increasing velocity profile. The outer gas has a shallow, higher magnitude velocity. In the later stages of the collapse, the core develops supersonic speeds. This is before the construction, or before the emergence of the singularity, which represents the star formation. This is in direct contradiction to the general picture that low mass cores have subsonic motions, and we'll see why our work basically overhauls this picture. The density and velocity profiles of the various time steps during the simulation are shown. On the left is the density with the radial distance scaled by the gene's length, and on the right we have the velocity, the sound speed, against the radial distance, again scaled by the gene's length. So the simulation develops radial velocity profile naturally right from the initial state of the collapse, which, although unstable, is initially at rest in the background flow. The core starts with an amplitude with a density 50% more than the background, so its density is 1.5 by 10 to the 4, where the background is 10 to the 4, higher than the density of the background unstable cloud. The core is defined where the radius emerges with the background. This is the background, and the cores tend to be defined here. It grows in mass and density over time. So the radius increases and the mass increases. This is quite different to previous numerical setups. Most recently is Staller and Mohammadpour 2013. The simulation differs from that, where they consider a constant accretion rate. So ours has an accretion rate which changes over time, hence the outer radial point and the mass change with time. Previous velocity assumptions in these cores, is that me? No. Okay. Optically thick or opaque lines of non-homologous cores tend to show blue skewed self-absorbed lines. And we'll show some examples of that in a few minutes. However, to be a plausible collapse candidate for observed cores, you need to show two features simultaneously. First of all, a blue skewed self-absorbed optically thick line and a Gaussian-like optically thin line peaking at the self-absorption dip. The actual optically thick line doesn't have to be quite Gaussian-like, but if it's skewed, it must be skewed to the source velocity or source systematic velocity. Earliest assumptions on the velocity profile include that of the inside-out collapse, which was due to Frank Schu's model, single isothermal sphere, 1977, whereby you have the greatest velocities in the inner part of the core, the lowest at the envelope or the outer parts of the core. However, this has recently been deemed unrealistic since the singular isothermal sphere is completely unstable. It doesn't occur in nature, and it should never occur. So the Schu model is flawed. Other suggestions for the velocity profile, the radial velocity profile, include this simple two-layer model from Philip Myers, 1996, where you have two slabs falling towards one another, each at a velocity of the velocity of the core, or the velocity of the infalling gas. So the relative velocity is twice the infall velocity of the gas. And the initially unstable Bonner-Ebert-like sphere from Eric Quito, 2015. In the latter paper, Quito looked at the non-equilibrium Bonner-Ebert sphere and the quasi-equilibrium Bonner-Ebert sphere, whereby the quasi-equilibrium is in equilibrium each phase before as the collapse proceeds. At any one time, it can be seen as an object in equilibrium. The non-equilibrium Bonner-Ebert sphere is more like the Larsen flow, and more like our flow too. However, he artificially increased the density at all points in his model. Hence, his conclusions may again be problematic. So, his conclusion was that for the low mass Stardust core in Taurus Auriga, L1544, that the observations in the H2O 110 to 101 transition and the CA2 1 to 0 transition, the quasi-equilibrium Bonner-Ebert model can match both the line width and strength of those particular lines. They're recent observations from 2014. Oh, I'm here, man. Okay. So let's look into more detail on the Raoult's model from 2015. It's an isothermal core gas, temperature of 11.4 Kelvin. It's initially at rest, as I said before, with a uniform density of 10 to the 4 per cubic centimeter. The fluctuation has a density of 1.5 by 10 to the 4, but the background medium mean density of 10 to the 4. This makes the sound speed of the order of 0.2 kilometers per second. Using this density and temperature, the gene's length is 0.22 parsecs, where our assumed mean molecular weight is 2.36. The boundary length of the box is 0.71 parsecs per side. This results in an overall mass of 207 solar masses, which results in about 31.6 genes masses. The original grid resolution is 512 cubic cells. However, for the synthetic spectral production, we don't consider the full box because it requires a lot of computing power. So instead, we focused on an inner sub-box. And the sub-box has a central half-length, or a volume of 0.047 or 0.05 parsec cubed, which is just the half the boundary length cubed. And again, like in all synthetic spectral production, you must center your box on the highest density voxel, which for this very simple simulation is at the center. The sub-box is 256 cubic, and it has a spatial resolution of 1.4 by 10 to the minus 3 parsecs. What was that? These are the time steps which were considered in our analysis. So these time steps are very close to the production of the singularity or the star. 65 represents the formation of the star, and we considered these 7 time steps. This is the evolution in mega years. The free fall time since the beginning of the evolution of the fluctuation. We also have the maximum velocity in both terms of the sound speed and in kilometers per second. As you can see, at time step 55, we have a supersonic flow. And the position of the maximum velocity gets increasingly closer to the center. So we used Eric Kito's MOLI code, Molecular Line Explorer. The MOLI code is non-LTE. It is very useful for modeling the small-scale structure of simulated gas. It doesn't have the large velocity gradient assumption. It doesn't either consider the microturbulent assumption, and hence it's very useful for what we're trying to do here. Within the code, we use the HCO plus transition, 2 transitions, which represent our optically thick lines. The critical density, of course, ranges as the cube of the frequency of the 2 lines, J1 to 0 and J3 to 2. Higher critical density gas can be used to trace the innermost regions of the core. Even though our core is artificial, it still produces the largest densities at the center. Also, HCO plus is more useful than the other optically thick tracers, such as CS and H2CO, in that its dipole moment is greater than that of each of them. This means that it tends to predominate further out into the envelope gas, where the highest velocities, as we will see, tend to be. So this is why it's a more useful tracer than CS. The low optically thick or the optically thin tracer we used was the hyperfine line from N2H+, diazenillium. This particular line remains Gaussian-like throughout the collapse. It was important that it remained Gaussian-like at the last time step. Now it doesn't remain sufficiently Gaussian, but it has a slight skew. It still can be used as the optically thin tracer. The densities or the abundances that we used are typical of low to intermediate mass cores. The output from the radio transfer code was convolved with the following beam sizes, all in parsecs: 0.015, 0.03, and 0.06. 0.06 still represents 1/6 of the original box, and it can still trace most of the small-scale structure. So these are particularly useful beam sizes to convolve with our setup. Although they do translate as, this is 22 arc seconds, so it's very coarse when you consider the abilities of ALMA and EVLA, etc. These are our results. In this plot, you can see we have an optically thick or self-absorbed line profile from HCO+. These are the 3 to 2 lines, which produce greater self-absorptions than in the case of 1 to 0, due to the fact that it has a higher critical density. The dot dash line is the corresponding 1 to 0 line from N to H plus for the same position. We considered 5 positions from the core center out to the envelope. We also fitted the self-absorbed line using the Hill 5 hybrid model from Christopher de Vries's paper in 2005. 5 stands for the number of parameters which are derived from the fit. These include the line with dispersion, the systematic velocity, the optical depth, peak temperature of the self-absorbed line, and the in-full velocity, which remarkably are of the order similar to the order found by Chang-Won Lee in 2001 for low mass cores, around 0.1 to 0.15 kilometers per second. So although these particular time steps, 57 and 61, as we saw in the previous table, produce supersonic velocities, their line profiles don't, or the results from the fitting of the line profiles don't. Hence, the conclusion that such cores, such low mass cores and intermediate mass cores, can be considered quasi-static at any stage is flawed. Our provisional conclusions is that it's flawed. So if it's based solely on an observational viewpoint, then it's flawed. Yeah, that's from this. Right, you go. Okay, yeah. This is from comparing the velocities with the Chang-Won Lee survey from 2001. The outer velocities are smaller, obviously, because you're changing the line of sight. But this is the particular line of sight we care about, the one towards the center of the core. We also looked at the Mardones parameter from Diego Mardones' paper 1997. This calculates the skewness of the blue peak, basically how shifted this peak is from the optically thin peak. The values are provisional; they need more work, but they're within reason. They're close to what you would expect for a high density infalling core, a prestellar core. A core can only be considered to be infalling or in a state of collapse if the Mardones parameter is greater than the 0.25. And in all cases, for the two time steps we're considering here, we have magnitudes of delta V greater than 0.25. Another parameter, these are just selected results from the work, which is ongoing, close to finishing. We have the TB-TR ratio, which is the ratio of the peak height here, of the blue peak to the red peak. So just the ratio of that. Now, the values produced from the two transitions are different. The 1 to 0 transition wasn't as self-absorbed as we would have liked. And the reason is because of the background density of the simulation. The background density is 10 to the 4, so this self-absorbed peak, or the self-absorption trough, is relatively high. And it was very high for the HCO plus 1 to 0 due to its critical density. In the 3 to 2, the troughs were more pronounced, but only when you get close to the end of the simulation. So for 61, 62, or 64 and 65 in our simulation, do the troughs get remarkably pronounced. The latter time steps tend to be a little bit a little bit saturated, and that's because we didn't consider an abundance profile, which people tend to do in modeling low mass cores. We just considered the abundance constant from the envelope edge all the way to the core center, and that's why we have these slight saturation of the blue peak compared to the red peak. So it's almost a rose signaling profile, but not quite. Doesn't get there yet. The thing here is that these values, especially for the 0.015 beam size, are similar to what is found in low mass cores, especially in Taurus Auriga and Ophiuchus, L6942 and L1544, both in the LINS catalogue, are classified or have been observed to produce what are called extreme TBTR ratios of the order of 3 or above. Now, we are able to produce such ratios quite naturally from our simulation. However, as you can see, once the line saturates, the TBTR peaks and then drops below 1 for the later time steps. So Stephen Steller and Jeffrey N. did say in 2010 that numerical models up to that point were not able to reproduce observed TBRT ratios. It's quite satisfying at this point, at least, that we can produce at least values greater than 3. There are cases, protostellar cores, B335 and B133, produce values of the order of 5 or 6. So we're not able to produce them with this particular model, but that may be down to due to the background density that we assumed. Finally, the conclusions. The main one being that these apparently subsonic velocities that are derived or deduced from observational data may be an artifact of the assumed radial velocity profile. We use the Hill 5 in our analysis of the synthetic spectra, but the two-layer model that was used previous to 2005 is quite simplified, and we think that aspects of that have led to people to believe that these cores are subsonic and hence quasi-static in nature, especially in the pre-stellar phase. Our core, simulated core, collapses outside in, highest velocities external in the envelope, and the maximum speed at the envelope, not in the center as was envisaged by Shu's 1977 paper. As line profiles are density weighted line of sight velocity histograms, the maximum velocities are missed by the beam, because the peak velocities in the earlier stage of the simulation are simultaneous with what we consider as low densities, less than 10 to the 5 by 10 to the 4 in the case of our model, which is close to the background already. So in that conclusion, we're stating that the reason why observations or this subsonic idea is floating is because the maximum velocities are being missed by relatively coarse beams. The core is able to display well-publicized values of the Mardones parameter, delta V, and provisionally at least, it's able to reproduce observed TBRT ratios towards low-mass cores. And gracias por su atención.
Thank you for bringing us closer to our local environment. Any questions? Yes.
Are there any observed line profiles that are comparable to what you calculate?
Yes. The only issue that our simulation has is that the background density is high. We're directly comparing our simulation to low mass cores, where the density is of the order of 10 to the 3 in the tenuous part of the envelope. So our background is probably a little too high. Although we can repeat the same project with a lower background density. But from the perspective of fitting the lines and getting derived values, the values are similar to what's seen in the observations. Yeah.
Yes, just hang on a second for the microphone. Okay.
Yeah, I was just a little bit confused about the models, the dynamical models. So are they actually spherically symmetric, or is the background that they're evolving in not symmetric? Because like those velocity plots that you showed, it's just a V, so it's hard to tell.
It's symmetric, but that velocity profile is self-reversed, isn't it? So it is a spherically symmetric inflow.
So if it's spherically symmetric, would it not be easier in terms of like your resolution, where you had to like model just a smaller fraction of the system, to just do it in 1D, and then you can go really high and just use the symmetry of the problem?
Indeed, and the original Passat and Vasquez-Medini's paper from 1993, 1994 was a one-dimensional simulation.
Yeah, I mean, you should be able to, even with your extra dynamics, be able to do that. And
Yeah,
get
it
the
would be
same stuff.
straightforward. Yeah. It's a very symmetric employment.
Okay, is there a last question? If not, then we'll thank Robert again. And we come to the last, but by no means least, talk by Deborah Dultzin, who will take us back into the domain of quasars.
With radial velocity. Yeah.
Are you giving a talk?
No.
Oh, okay. It's setting I'll give you a 10-minute warning, but I don't think the time's a problem. So, when there's 10 minutes left, I wave.
And then let me put it in my wrist. No, my waist. I think it's siesta time for me. So if I sleep during my talk, I'm sorry. Okay.
You need to go back.
I need to go back. I don't see anything. Yeah. Okay. The thing is that the first author is Mariloli Martínez-Paredes, and she's a former student of mine, but she's now in Granada, so I will be giving her talk. And I think I'm coming back to the topic of this session. So I'm going to talk about the low ionization broad emission lines in intermediate quasars, where intermediate is the most relative thing in the world. Low Z, high Z, it depends to whom you're talking. As you've heard in previous talks, in many respects, the emission of iron is very important, particularly in the optical and ultraviolet spectra of AGN. And to us, it's very important, among other things, because it produces a sort of pseudo-continuum that has to be taken into account in order to perform accurate measurements of the broad lines. Now, one thing is to study narrow lines, and another very different thing, as you heard from Alenka's talk, is to study broad lines. We believe that the iron 2 line has not been very, why don't I see it here? Because Alenka, I don't see my talk here. No, but I need to see my talk here. Otherwise, well, as you see, this is an age where I don't know how to do anything. But fortunately, at this age, one has students. So I will not see it here. Oh, dear. Oh, well, anyway, okay. So sit back and relax. Well, so one of the problems is the complexity of the iron 2 atom, and also the fact that it is pumped by fluorescence processes, the iron 2 line, and they are difficult to consider within a photoionization code. And also, because it's emitted in a partially ionized heated zone, as Sylvain explained, and though it is through non-local processes. So the photoionization models have problems in producing the strong iron 2 emission because it's a strong coolant of the photoionized broadline region, and the ionization parameter cannot be too low because otherwise there will not be enough ionizing photons. This was already pointed out What? Will you do this every time for me?
No.
Oh, no. ¿Qué pasó? Okay. So Fred Hammond said it was the first time he showed the Gaussian diagram in a meeting, and now this is the second time in the same day you see a Gaussian diagram of Fe2, just to show that it is horrible, really horrible. I'm sorry, Gary, but for me it's horrible. However, the calcium 2 ion and the O1 atom can be modeled with only 5 levels. So what is the relation? What does it have to do with iron 2? Well, I will show you. Point is that a long, long time ago, well, first of all, let me say again that the iron 2 strength is one of the parameters of our 4-dimensional eigenvector 1 space for broadlines. And a long time ago, we realized, by chance more or less, that the calcium 2 emission follows the same trend as the iron 2 emission. The problem is that the data at that time were scarce and plainly bad, horrible. If you realize the error bars, will I possibly be able to use this? Where do you point? Martin, where do you point? You don't know either? Oh, okay. I got the wrong pointer. Fine. So, okay. There are very few, the advantage is that there is very little work on this. You don't have to read a lot of papers. Actually, the theoretical work, as far as I know, is only Monique Joly, Ferland and Persson, of course, and more recently Masuoka and Land. Land and company, I think you are part of this, yes? Have observed, however, mainly, well, you focus mainly on the O1 line. Okay, from the point of view of observations, it's Grandi, Persson, and more recently Rodriguez, Ardilla, Matsuoka, and again Land. Okay. Now the complications, observational complications, are large because it's in the infrared, because the equivalent width is very low, so you need large telescopes in order to have decent data, because very often these lines, the calcium triplet is totally blended. The region is contaminated terribly by the horrible telluric lines. And the continuum has a contribution, first of all, of the thermal emission from the disk, but also from the hot dust emission, and also from the host galaxy in this range. And from the host galaxy, by the way, we took away everything. Fortunately, iron 2 is not so strong in the infrared range. In order to subtract the host galaxy, we had someone, Alessandro Bressan, who made population synthesis models for us because there were none in this range. And our sample is complementary with that of Persson. He selected strong Fe2 emitters. Only 5 of his objects were calcium 2 emitters and low luminosity and low redshift. We selected high luminosity objects. We observed with a very large telescope and a spectrograph named ISAC, which is no longer there. Well, they have a better one. And all of our objects show these lines, but we only took those which were not terribly contaminated with the telluric. Okay, this is an example. This is the H-beta data, our own data from Sulentic, Marciani. You can see here how strong iron 2 emission can get. It depends on the type of object. This is a very nice spectrum where the calcium 2 triplet is not blended, and this is the O1 line. Here it's totally blended, but anyway, of course, our spectra are much larger. We have passion 9, 8, 9. Okay. Now, we also use this type of multi-component fit, which I insist that is very important in order to fit and measure broad lines, otherwise you really don't know what you're doing, or you obtain uncertainties bigger than the lines. And for the optical spectrum, well, we made the fittings according to Marciani and company. I am part of the company. And for the near-infrared spectrum, we measured O2, the triplet, the passion 8, the passion 9, etc. Well, I won't go into details. Anyway, the first result is that we did confirm totally with this sample that there is a correlation between the emission of iron 2 and calcium 2. They follow exactly the same relation, and from this we can infer that the two lines are emitted from regions with similar physical conditions, which was pointed out by Monique Joly as early as that, well, or at least suggested. Ya se atascó. Okay, thank you. Thank you. What would I do without students? My God. Okay. So we used cloudy models to reproduce our observations and see what are the physical conditions. We use the Matthews and Fairland continuum. We use this iron 2 ion, a large range of densities, a large range of ionization parameter and column density. No, 2 column densities, I'm sorry. 10 to the 23 and 10 to the 25. And we got the equivalent width of calcium 2 or 1 and these ratios, okay? This ratio comes from the same spectrum. Okay. So, what do we get? We get that the calcium 2 is emitted in a range of very high densities. As you can see, 10 to the 11.5 to 10 to the 13.5. And this is in agreement to conditions argued for iron 2. Maybe both of these ions are emitted on the outer part of an accretion disk. This was suggested by Susie Loughnane and by Monique Joly. Now, the O1 line, however, can be emitted in a high density regime. Part of it goes to 12 point I don't know what, but also it reaches the regime of the H-beta emission. 9.5. Oh no, this is not 9. Well, anyway, it goes down to 9.5. So, what does this mean? Before I say what does this mean, oh no, I wanted to say also that, you know, the dynamics of the region that emits the lines is deduced from the profile of the line, which, as you have seen in the case of broad lines, it can be analyzed. Of course, if you have high signal to noise, good resolution spectra, which is not always the case. With our sample, we find that the dynamics of the O1 line is the dynamics of the region that emits the line is the same as the dynamics of that is the full width at half maximum is the same, although the physical conditions may not be necessarily the same. This can be explained how? If the regions have slightly different physical conditions, but of course are at the same distance of the ionizing source, black hole or whatever. So, because the full width, for the people that don't know what a broad line is produced by Doppler. Okay, so this is a cartoon, totally cartoon, which I made with some help, of course. Look at my observer. It is very Egyptian. So, the point is that although the physical drivers of what we called, in 2000, we called the main sequence for quasars are mass of the black hole and accretion rates, or Eddington luminosity as you wish, these are the main drivers of this sequence. Orientation, of course, plays an important role, particularly for the stream viewing angles. So everything this is not a puffed accretion disk, it is very cartoon. Everything that comes out from the disk is enhanced. The inner part is the soft X-rays, probably iron, calcium is enhanced from this point of view. And of course, the full width at half maximum of H beta is smaller. These are actually the so-called narrow-line Seifert 1 objects. And of course, this is another topic. Carbon for the higher ionization lines are seen with large blue shifts and blue asymmetries. These clouds are virialized, so they are also due to Doppler broadening. The O2 can be emitted in the back part of the cloud, which is partly shielded from the radiation. And from this extreme viewing angle, we see what we call population 2. The largest widths of H beta, as large as many thousand kilometers per second, etc. So, I think that's all. Oh, my conclusions, our conclusions. So we computed an array of simulations using Cloudy that covered a large parameter in space density and ionization parameters in order to determine the physical conditions of the region that these ions are emitted. We found a very high density indeed is needed for the emission of the calcium-2, just as iron-2. We found consistency with the hypothesis that iron-2 and calcium-2 are emitted on the same physical conditions, and probably the outer part of the accretion disk. what is this in preparation? So all these models were done using clouds. But presently, we are working on a disk, a Shakura-Sunyaev accretion disk. Well, the equivalent weight suggests that there may be, I didn't speak about this, but if anyone is interested, I have another slide. There might be chemical enrichment in the broad line region from a recent starburst at high redshift, although it could also be a selection bias. NO1 may be emitted in a wider range of densities, of densities. Okay, that's all, thank you.
We have time for some questions. I'll start with one, and that is, I think this association of the calcium triplet with the Fe2 has been around, as you say, for some time. I'm interested to ask if there's any evidence in support of a claim, I think a few years ago, from a Chinese group that did a very big survey of narrow-line Cfoot1 spectra from the SDSS, who claimed, and I think the evidence was a little bit marginal, that the Fe2 was infalling, it was redshifted with respect to systemic. But then it should be easier to tell that from the calcium triplet. Is there any evidence for infall from?
Well, I vaguely remember this paper. No, the answer is no. The problem with the paper by the Chinese groups who do fantastic work, or people that work with thousands of data, as Sylvain pointed out, we knew about the dove a long time ago. That separates H2 from AGN. When you see it with thousands of data, it looks much nicer, but sometimes we don't really learn anything more fundamental. So I don't know much about this work, but with our data, there's no...
Yeah. Well, as I say, it was a bit marginal, but it would have been interesting if the Fe2 was infalling. But
we will keep looking for it because we have a lot more data to reduce. But you know, students have to get a degree at some point in their life. So
yes, quite okay. Any questions? Any more questions? Yes. Hang on a second.
What? Oh, my eyes, they're beautiful. My eyes.
Where did you get it from?
To tell you the truth, she did it for me. Yeah, and there are the angles they should be. Look, you can do this beautifully nowadays if you have a student. So look. It is about 30 degrees. It cannot be like this because this is a Veilleux. Yeah. But more or less like this and like this. I usually put eyes with eyelashes because I like women observing. But these are beautiful, I think.
Very artistic indeed. Well, we can leave it on an artistic note. I'll give you one chance for any more questions. If not, I'd like to thank Deborah and all the speakers this afternoon, and have a good evening.
Ay, sí, pero no, vamos a hacer la excepción y no la regla, porque no la gente ya no va a ir a congresos y todo va a ser por Skype. No, es lo que me decía mañana. Es la primera y única vez. No lo van a, no es buena idea. La gente tiene que estar, si no los congresos ya no van a tener. O sea, todo el mundo puede decir, quiero presentar algo. No, entonces ya para qué haces congresos en lugares bonitos, para que se reúnen la gente.
Le dije, conéctate para las preguntas. Dijo, no sé si
Está bien. Bueno.
know that the boss will leave at 5:30 today. The boss will leave at 5:30 today because we're finishing earlier. Yes. Okay. Okay.
Good sharing. Job done on budget on time.